Hello, my name is Leonard Kleinrock. I'm chairman of the Computer Science Department at UCLA. We have here a really exciting and dynamic environment. And one of the activities that contributes to that environment and that excitement is the constant flow of visitors who come and spend time with us and interact with our faculty and student body. Each year, we select a few from among the very best researchers in the field and ask them to participate in our distinguished lecture series. The high point of their visit is the presentation of a lecture to our faculty and student body. And at that lecture, they present the state of the art in their field of specialty. They describe the research results, the open problems, and the directions in which the field is likely to go. And as you might expect, these lectures always generate a great deal of enthusiasm and interaction. I'm really pleased you've chosen to join us today. Let's go inside. The lecture's about to begin.
Welcome to the last of our distinguished lecture series this academic year. Last chance to get the glimpse of one of the giants in our field. Today we have Ed Feigenbaum. I've known Ed for 1,000 years. We first met, I believe it was in the good old days, when you could get all the DARPA principal investigators into a room the size of a small ski lodge overlooking the ski slopes and conduct a meeting and actually have the attendees stay and participate. A lot of years ago, in the late 60s. Ed is a member of 2 academies, Academy of Arts and Sciences, National Academy of Engineering. Now, as you know, I like to give a little description of what motivates a giant such as himself, a gentleman who in fact invented expert systems, reduced it to practice, basically laid down the seminal ideas, now at Stanford University. So let me just go through a little bit of the background. No, it's a little different today. Don't get frightened. Today, Ed himself is going to say a few words about what turned him onto this field and the kinds of things that might turn you onto the same field. So let's hear about expert systems of the future. Ed, join us.
Well, this is a very unusual event for me, for Len to ask me to review a little bit of personal history. It turns out that it was not a difficult thing for me to agree to do because, as it happens, I did a personal history of my professional development leading up to expert systems for a keynote speech that I gave at the first World Congress on Expert Systems last December. And I happen to have a copy of that paper with me. So what I'll try to do is to briefly skim the opening pages of that personal history and try to give you some highlights. Not because it was part of my prepared speech, but because the chairman asked me to do it. Certain aspects of my background, my education, and my early professional development set the stage for the innovations I made that led to expert systems. And I would like to tell you about those because normally when people talk about innovations, they talk about them as if they were Athena, born fully clothed from the head of Zeus. And that's not the way things go. In fact, each innovation has a context in some person's individual personal development. As a child, I was fascinated with science and with mathematics, and there's nothing unusual about that. But I was also fascinated with calculators, and that was quite unusual in the 1940s. I was born in 1936. When I talk about being a child, I'm talking about age 8, 9, 10, formative years. My father was an accountant. He owned a large, heavy mechanical calculator. Actually, it was a Monroe calculator. It weighed about 30 or 40 pounds. With a motor that turned number wheels, a carriage that had to be shifted one position at a time by hand, and a very large numeric keypad. He taught me to use it expertly, and I proudly carried the heavy bulk of that thing on the school bus back and forth to school to exhibit my prowess to my friends, who really couldn't care less. In 1952, I entered engineering school at Carnegie Institute of Technology, now known as Carnegie Mellon University. The only calculator that I saw at Carnegie Tech until 1956 was my own slide rule, which I now keep in a fireproof safe because it's so valuable. Probably half the people in this room don't know what a slide rule is. When the rigors of the freshman engineering course was over, I felt the need to stretch my mind beyond the traditional bounds of the engineering curriculum. So I looked around in the catalog for sites of interesting activity going on at Carnegie Tech. And I found that there was a new school there, just had been formed, called the Graduate School of Industrial Administration, which had some very interesting courses. A course in game theory, which I took, and there was some research activity in decision making. In 1955, in the fall, when I was a senior, I took a course from a person named Professor Herbert Simon. Of course, now you all know Simon as one of the founders of the field of artificial intelligence, Nobel Prize winner in economics in 1978. He was giving a course on mathematical models in the social sciences. And I took that little course. That course was a seminar that had 3 people in it. And that was a turning point in my life. In just after New Year's, 1956, Simon came into class when we met right after the New Year and announced to the 3 people in the seminar that over Christmas, he and Alan Newell had invented a thinking machine. Now, that really came as a kind of an oxymoron to us students, although we didn't know the word oxymoron at the time. What does he mean by thinking and machine? They don't go together. Well, thinking is intuitively obvious, and for machine, he gave us a copy of a manual. It was a manual for a machine called the IBM 701. It was a vacuum tube computer. It was IBM's first entry into electronic data processing. The RAND Corporation here in Santa Monica had one. Alan Newell, his colleague, working colleague, was using the RAND 701 with the help of a person at RAND, Cliff Shaw, the Shaw of Newell, Shaw, and Simon. And over Christmas, Newell, Shaw, and Simon had conceived of how to program the logic theorist, the first heuristic program, a program that proved theorems in the propositional calculus. I remember taking that 701 manual home, and I stayed up all night reading it. It's just vividly emblazoned in my memory. And by morning, I was a kind of a born-again, well, what we now call a computer nerd or computer scientist, except there was no term computer science until about 1964. But in any case, I realized, having read that manual, that that's what I had to do. That was the most fascinating thing I had ever read, and I just kind of read into it a whole bunch of implications, all of which have come to pass, have been the case. So there was nothing at Carnegie Tech that I couldn't deal with it. There was no computer there. So I signed up for a summer program at IBM in New York. They were running their first program ever for assembling graduate students for the summer to teach them about computing. And I went to New York with 29 other people in this 30-person program, and they taught me how to program the IBM 650, which was a small computer with its random access memory was not quite random. It was a memory drum of 2,000 words on the drum, 10 digits per word. The drum had to be optimized. And they also taught me how to program the IBM 704, which was the follow-on machine with index registers to the IBM 701. Now, in that period of time, while Newell and Simon were pioneering the logic theory program, John McCarthy, at the same time, had created a word for this new field. He called it artificial intelligence, and he and Minsky ran a conference on it in the summer of 1956. That was the so-called Dartmouth Conference that myth has it launched the field. So my decision was simply to go back to Carnegie Tech and continue to work with Simon and Newell on my doctorate. I just couldn't imagine anything more fascinating than that. Just to give you a feeling for what programming was like at the time, symbolic assemblers had just been invented at that time. There was one called SAP for the 701, 704, and one called SOAP, where the O stand for optimizing, for the 650. And there was a new concept that we heard about when a computer guy came downstairs from the 4th floor of our building, John Bacchus, now of course famous John Bacchus, came down to tell us graduate students that there was a wonderful new way to program. You didn't have to program with things like clear and add. You could actually write formulas. And the name of this language was formula translation, or Fortran for short. Well, when I got back to Carnegie Tech in the fall, Alan Perlis was there with a 650, and there was a compiler already there. It was Perlis's IT compiler. There was also work on the invention of the list processing languages by Newell and Simon and Shaw, 3 years before McCarthy invented the notation for Lisp. And there were two kinds of activities going on that now we lump under the term artificial intelligence, but then were separate activities. One was called computer simulation of human cognition. That was the attempt to construct very detailed models of how humans processed information in symbolic learning tasks or in problem-solving tasks. And then, of course, there was the activity of building programs that would do intelligent things, whether they did them with verisimilitude to human activity or not. Simon, of course, Simon was my mentor, and as is the case with mentors in all ages, in all places, mentors give students good problems to work on. So as soon as I got back in the fall of 1956 and said, okay, here I am, Simon gave me this problem, which was to analyze certain kinds of data from human verbal learning experiments, rote learning experiments, and to try to conceive of a set of information processing mechanisms that would account for this fundamental data that had been accumulated over a period of about 50 years in psychology. And that model that I created was called EPAM, for Elementary Perceiver and Memorizer. It was, in a sense, a pure attempt to use information processing techniques of AI for psychological modeling. This work I found very exciting and rewarding, but in the deepest sense, I found it unsatisfying, because it failed to satisfy my most basic motive, which grew out of my early fascination with the calculating machines, the motive of building highly competent, intelligent machines. That's the motive that I now refer to as the performance motive in AI, as opposed to the common sense reasoning motive or the learning motive or the natural language understanding motive, the performance motive. These machines have to be world-class in what they do. This vision entails this is a vision with deep engineering aspirations. That is, less theory, more system building. So even in my earliest period of work in AI, the seeds of my work in expert systems, which were to generate later, were already planted by virtue of this motive. Now, let me just quickly conclude this portion of personal recollections by mentioning a few other things that were going on. Newell, Shaw, and Simon were conceiving of and programming the general problem-solving program. That was the most famous program of AI's first decade. That was going on. They were also, at the same time, conceiving and programming the Newell, Shaw, Simon chess-playing program, which was the first big flowering of chess-playing programs. The first public list processing language, IPL5, was released for the IBM 704. I wrote most of the code for the interpreter for IPL5. All around me in the Graduate School of Industrial Administration, there was economic theory and behavioral science theory being created. To give you an idea of what the environment was like, 3 of the people who were in that environment at the time have since won the Nobel Prize in Economics. Modigliani and Mert Miller, who won it a year, not the past year, but the one before that, and Herb Simon himself. 3 Nobel Prizes out of that small group of faculty in that brand new graduate school in those few years. An absolutely astonishing, incredible environment of innovation, achievement, excellence, and challenge to graduate students. Now, the story, I want to just draw together some threads before I leave this topic for you to take back with you. I think it is very rare to experience life at the center of what is essentially an intellectual supernova. As I re-experience this by reflection and in retrospect, it's an amazing experience. But it's only in retrospect. Strange as it may seem, it is difficult to understand and to savor it while it is happening. While one is living it, one adapts to the extraordinary as if it were the usual. Now, in my career, I've had the incredible luck of having this occur twice in my career. Once at Carnegie and once at Stanford with the invention of Dendral with Joshua Lederberg. The second time is no different than the first time. That is, only in retrospect could you realize what an amazing event had occurred. I worked through this early period, and I was teaching at Berkeley for the years 1960 through 1965, away from the direct influence of Simon and Newell, and I still found that particular path I was going down satisfying. EPAM and the other work on information processing models of cognition were not lined up with my dream, the dream of the superintelligent machine. I did not resonate with cognitive psychologists. I resonated with those people who were beginning to be called computer scientists, and particularly with the engineering approach. I believe it is very important for young people to sense these directions and mismatches early in their career and to head in the direction of their dreams. And I advise you all to do that. Now, today, what I'd really like to talk about is knowledge. AI's approach to knowledge. I'm going to discuss knowledge really as a drama in 4 acts. You might think of these transitions as AI, the science, AI, the technology, and how the science and the technology deals with knowledge. The activity is a kind of a romance. AI discovers knowledge. There's a beautiful romance. They have wonderful kids. The kids do very well in the world. But 25 years later, strains appear in the marriage. And so AI and knowledge have to go to work again to expand their horizons, see what new activities they can do together to keep the marriage solidified. So let's look at Act 1 of this drama. What do I mean by knowledge? By knowledge, I mean something fairly specific. I mean a high-level form of factual and heuristic conceptual knowledge. Now, I'm willing to include some low-level knowledge in the definition of knowledge, so let me give you an example. In engineering, for example, we in engineering deal with the knowledge of physical laws, physical principles, also engineering know-how and engineering principles. That's the kind of factual and heuristic base of things that I'm calling knowledge. I'm also willing to call knowledge that which appears in engineering catalogs, which documents the kind of artifacts that we have available commercially and can put together into other artifacts. Let me give you an example of the difference I draw between knowledge and data. And again, I'll use an engineering example from the world of diagnosis or troubleshooting. General Motors has, to take 1 out of 10,000 examples of diagnostic systems for troubleshooting, General Motors has a system called Charlie, which models the diagnostic abilities of a superb analyst of machine failures detectable by modes of vibration. That is, Charlie could listen to things and he could hear what's wrong with it, whether those things are machinery for making cars or whether it's cars themselves. Charlie could figure it out. Well, Charlie had a great deal of knowledge about how machines were put together. He knew all about pistons and vibration tables and gears and gear wheels and cams. And I mean, Charlie knew all that stuff. And Charlie could translate that stuff into understanding vibrational modes of the equipment. He used to go around measuring the vibrations of equipment with some gadgets that he would carry around. General Motors actually sells this software now, and they actually sell the gadgets. And in fact, they claim that both the selling of the software and the selling of the materials and diagnosis of the equipment itself saves them or makes them $50,000 a day for this particular software system. The actual data that Charlie's vibration analyzer was accumulating, I would not call knowledge. I would call that the data of the problem. And it was Charlie's understanding of mechanical engineering that constituted the knowledge that was applied to analyze that data to come up with solutions to the problem. Now, programs have always incorporated knowledge. You can't write a computer program without building in some knowledge about the domain of work that you want the program to perform. But the AI community was the first to represent and manipulate that knowledge explicitly. Otherwise, it was just built into the code. The processing of that knowledge, and sometimes the discovery of the knowledge, was the essence of the AI computation that was actually going on. Now, what was behind that computation? What's behind that computation, whether you're officially a logicist or not, was essentially symbolic logic. Logic is a calculus for representing and manipulating knowledge. It existed a long time before AI became aware of the importance of knowledge. And so the AI research mainstream has always employed some form of logical, non-numeric processing based on the propositional calculus or the predicate calculus or some other higher order forms of logic. Of course, that position, that mainstream AI is essentially logic-based, is under severe attack from the so-called non-representationalists or from the neural net people. But it is the mainstream of AI. Now, prior to 1965, AI was concerned primarily with the computational process of problem solving. Let me give you some indications of that. That is, to put it bluntly, AI said in its writings and its work almost nothing about knowledge. It talked a lot about problem-solving processes, but almost nothing about knowledge. Newell and Simon wrote a classic, wonderful paper on their chess-playing program. It was reprinted in the first anthology that Julian Feldman and I did, Computers and Thought. I searched that early paper and found only one instance of the use of the word knowledge in a paper which was like 35 pages long. And that was an incidental instance. It had nothing to do with the mainstream of the paper. It was just an off-course use of the word knowledge. Or when they did the logic theory program, Simon carefully explained to me why they picked propositional calculus. The reason was it was pure symbols. The symbols didn't relate to anything. The P's, Q's, and R's of propositional calculus have no direct reference in the world. That was because there was no technology, no concept for how to handle knowledge. Now that was pre-1965. In 1965 came a program at Stanford. I was referring to it as my second great experience. The invention of a program called Dendral. Dendral was a program which solved problems of hypothesis formation in the area of organic chemistry. In particular, the analysis of spectral data called mass spectral data leading to the formation of hypotheses of organic structure. What we found, Lederberg and I and Bruce Buchanan and others found in doing this program was that it was not possible to accomplish our goal of high-class, extremely competent behavior in this task without feeding enormous amounts of knowledge to the program. Well, I shouldn't say enormous. Given today's, what we would consider a large body of knowledge today, it was not enormous, but for the time, it was enormous. An enormous body of knowledge of chemistry and mass spectrometry. The program simply had to know a great deal about its domain of discourse before any of the AI processes that we were trying to apply would work. That led us, to, excuse me, 3 years after the start of Dendral, to formulate what we call the knowledge is power hypothesis. And it said at that time, and ever since, that high levels of competence in performance by AI programs are due primarily to the knowledge that the program has about its domain of discourse, rather than the kinds of processes it is using to achieve its problem solving. Those are definitely secondary to the quantity and the quality of the knowledge that is given to the program. Now, it's a very easy hypothesis to understand if you just keep a little example in mind. We're very close to the UCLA Medical School. If someone in the audience right now got sort of radically ill, we would probably run you over to the hospital on the other side of campus. We would probably not run you over to the math department, where they have much better reasoners. Reasoning doesn't count when you're sick. Knowledge of medicine counts when you're sick. Now, Dendral launched a decade of system building experimentation in lots of different areas, mostly at Stanford, but not entirely. There were systems in medicine, like the famous Mycin system for infectious disease diagnosis, and some others at Stanford. A system in engineering to assist in structural analysis calculations. We did a piece of work in X-ray crystallography determining protein structure. We did some work in a brand new field, which was called recombinant DNA. It had just been invented at Stanford and UCSF by Boyer and Cohen. And we did some planner for planning experiments in genetic engineering. And then there were 3 pioneering commercial applications, 2 of which were mothered by our lab and 1 at Carnegie. The ones at our lab were applications by Schlumberger, leading to a later program called the Dip Meter Advisor, and 1 at IBM Palo Alto, leading eventually to an expert system tool called ESE, Expert System Environment, and then a spin-off into a private company of that. The company is Aon, and the spin-off was Aon Development System, ADS. So that's the end of Act 1. Act 1, AI flirts with knowledge, AI gets to love knowledge, they get married. Act 2. Act 2 is the story of the kids. So the kids come. Now, let me just tell you a few of these kid stories, because they're really great stories and they illustrate the knowledge is power hypothesis. They illustrate the importance of knowledge in the absence of striking developments in the nature of AI reasoning methods, computations for AI logic processing. In the absence of those, still, knowledge wins big. Let's take one of the old stories. You may be bored with hearing about it, but it's worth recounting. And that's the DEC system, Digital Equipment Corporation's XCON configuration system, initially for configuring VAXs, and later the PDP-11s, and later still most other equipment that Digital manufactures, configuring larger systems from smaller subassemblies. A very difficult knowledge-based combinatorial task. DEC did it. When I say DEC did it, it's really John McDermott at Carnegie Mellon. Later, John moved to DEC, and there's a big group now which deals with XCON. Probably a couple dozen people routinely deal with XCON and update. DEC did it initially on a vision of 2 of the DEC managers, one of whom is a man known for tremendous vision, Gordon Bell, that DEC, if it could configure these mini computers properly by what you might call pure thought, then they could avoid building 5 projected final assembly and test factories that they were projecting they would need to build in the 1980s for the growth of the number of VAXs they were selling. It used to be that they would build a factory like that, assemble computers in there, check it out, make sure the computer worked, tear down the computer, box it up, and send it to the customer. If the computer could be configured exactly right in the first place, there would be no need to pre-assemble it at the factory. You could just ship the parts to the site, and then the system engineer could assemble it. They actually saved themselves building 5 of those in the 1980s. The rate, the speed up of work in doing machine configuration was measured both by DEC and IBM later on when IBM created an identical program for their line of mini computers. The speed up was a factor of 300 over the speed that humans could do the same task. DEC said in a press conference about a year and a half ago, that XCON is currently saving them about $200 million a year. A very large amount of money. They also talked about the size of the knowledge base. We talk about knowledge is power. How much knowledge accounts for all this power? The answer is currently in the tens of thousands of pieces of knowledge about the interaction, about these individual subassemblies and their interaction. Not 100,000 yet, but getting close. That's a configuration story. Let me give you another one, which I heard just recently. I came back from a trip to Japan. We were doing an assessment of Japanese work in the area of industrial applications of expert systems. We visited a company basically on an intuition. I had given a lecture to a company in 1984. The Sekisui Chemical Company had a division called Sekisui Heim, where Heim is the German word for house. Sekisui House Building Company. Sekisui, the chemical company with a lot of manufacturing capability in plastics, but they also are one of the largest manufacturers of prefabricated factory-built housing in Japan. They also own a company, 21% of a company called Sekisui House, which is a competitor to Sekisui Heim. But what's their problem? The problem is, customer goes to the sales office, customer interacts with a layout program, looks at some pictures in the books, picks out a family of houses, like the Lumina family of houses. I want a Lumina-like house, but I want it to my specs. I want so many different rooms. I want certain features in the kitchen. I want certain features in the bathroom. I'm determining how much square footage and where the rooms are placed. Otherwise, you're going to make it in your factory. They sell me this house. The contract reads that they have to, the house must be completed in 2 months on my piece of land. The factory, the order goes, this layout goes into the factory the next day. And immediately they have to get to work in building this house. They have a parts picking problem because it's a unique house. It's custom made in a factory. That is, I chose the design. I chose exactly what I wanted. And they have to make it in the factory. So they have to decide how many 2x4s and how many wall panels and how many nails and how many different pieces of pipe and fixtures and typically several thousand things they have to decide on and deliver that stuff exactly to the right place at the right time on the line. You can imagine what kind of a combinatorial problem that is. When the Lumina houses are designed by the design center of Sekisui, a rule book is put out, which is, they showed me one, it's about that thick. And the people who do this parts picking have to master that rule book. Well, they basically, here, the problem is they get it right. If you're an expert, you get it right about 90% of the time. So there's about 10% error in this process anyway. When a new line of homes is introduced, it takes 6 months for a former expert to become an expert in this new line of homes, during which time they make so many mistakes that introducing a new line of homes is at the margin of being economically feasible. So that you're talking about something highly strategic for the company to make it possible to launch new lines of homes. Exactly what IBM found when they finally discovered why DEC had done a configuration program. When they brought out their mini computer line, they found out they couldn't do it without a configurator. Anyway, to make a long story short, the accuracy rate, even in the best case, has improved from the 10% error rate to now a 0% error rate in picking the parts. The actual saving is 1 billion yen per year, and that translates into $7.7 million per year. The number of things the system knows is of the order of 10,000 things. that it knows from those rule books, for each rule book. Just a few more examples from the kids. We ran into another one in Japan, a planning and scheduling knowledge-based system done by NEC for JAL to schedule people, namely pilots, co-pilots, and engineers, onto 747s and variants of the 747, variants of the long-distance 747, plus other planes that they have in their fleet, like 737s and other planes. You're talking about, for the long-distance 747s alone, 500 pilots, 500 co-pilots, 500 engineers. And adding all the other planes together, you get another 500 of each category. They have, in this system, they have 45,000 frames, each of which has several dozen different facts about the pilot and the routes and so on. 7,000 rules, 1,500 different types of constraints. And the program gives them a speed up in replanning the staffing of people onto the planes from a few days to a few minutes. So it enables them, for example, to recoup if there's been some disturbance in the planning. Flights need to be rescheduled or people get sick and so on. They can do that replanning very rapidly. In north of Los Angeles, there are two counties, Tulare County and Fresno County, each of which have implemented a system for following an enormous rule book that determines whether a person is eligible for welfare. That rule book, first of all, I mean, who masters that rule book? It's these social workers who are rather low paid and sometimes rather low motivated people have to master this enormous rule book, and they make a lot of mistakes. That's the least of the problems. Most of the problems is that they keep the people waiting a long time for a decision. They now have in Tulare, these are kiosks where the person seeking welfare comes and is interviewed by a computer program, a kind of an expert system consultant, and the person touches things on the screen to answer questions. Overnight decisions, reduced from normal 3-week decision to overnight decision on eligibility for welfare with a complete rationale as to why the person is or is not eligible for welfare payments. That system, the one in Tulare, has 4,100 rules. So we're not talking there about tens of thousands, we're talking about in the thousands. And the last system, let me mention, I'm just picking out those that have rather large knowledge bases. The IRS has a system called Taxpayer Assistant Expert System, TAES. The reason for that system goes something like this. On April 14th of every year, the news people always run a story which says, we called up the local IRS help number and asked them a lot of questions, and they were wrong 40% of the time. And then on April 15th, the IRS answers and says, that is outrageous. That is simply media misrepresenting us. We were not wrong 40% of the time. We were wrong 33% of the time. Well, this system, TAES, is an expert system to assist the person giving that advice, to reduce that error rate from 1/3 down to something much smaller. And tests done on this system in the Boston region, when they were testing it to see whether to introduce it into the other regions of the country, showed a reduction in wrong information being given to citizens from the 33% down to 3%. That's quite significant. And there you have, again, tens of thousands of things that the program knows. So keep in mind tens of thousands. That seems to be a sort of a big number for first-generation kids in this expert system world. By the end of Act 2, we could feel confident in changing the knowledge is power hypothesis shedding its hypothesis status. And it's now called the knowledge principle. The first really substantial empirical principle in AI. That is, what counts, if you're looking for power in knowledge-based systems, in AI performance systems, you get that power by pumping a lot of knowledge into the system. You don't get that power by, let's say, as the Japanese fifth generation project would have it, by pumping tens of millions of logical inferences per second. That's not the way to go. The way to go is by pumping tens of thousands or hundreds of thousands of pieces of knowledge. Declarative knowledge, rule-based knowledge, or descriptive knowledge. Now, let's talk about Act 3, the strains in the marriage. The problems. The visions, the aspirations, and some of the advances that have been made. What we're doing is we're passing out of the 1980s into the 1990s. That's what I'm calling Act 3. The two biggest problems that were faced by the first generation of expert systems were problems of narrowness and brittleness. Let me switch over to this thing. This is a diagram which is supposed to indicate. Maybe can I borrow one of that thing? What's in the black is the narrow specialty of an expert system. And the essential feature of an expert system is that in order to pile up enough knowledge to make a difference, given the knowledge principle, you had to keep the focus narrow. You couldn't try to codify the world. It would be enough to codify infectious disease diagnosis or structural engineering calculations or whatever. Expert systems are almost by definition narrow. Their performance level may exceed the performance level of the best humans in the task, but they are very narrow. Now, outside the bounds of narrowness, you find some additional knowledge that could be useful in solving these problems, but in fact is not used by expert systems. Let me give you a hypothetical example. Len was telling me today that he used to have a 1963 automobile which he cherished until it was stolen here in LA. Well, I'm the same kind of person. I like these old artifacts, and it happens, believe it or not, that I own a 1958 vacuum tube stereo hi-fi amplifier. The first Fisher amplifier that was ever done in this country. I bought one. I had just gotten out of graduate school. I bought one and still have it. If that malfunctioned, then I took it down to the hi-fi repair shop. The young guy at the hi-fi repair shop is expert at one thing only: prying out integrated circuit chips out of a board and sticking in another integrated circuit chip of the same number. Not only could he not debug a transistor amplifier, which I also have incidentally, but he wouldn't even know what the word vacuum tube was. And he doesn't know any Ohm's law, and he doesn't know any Kirchhoff's laws, and he doesn't know anything about circuit analysis. So I don't take it to him. I go down to another shop where I find a guy who's about 65 years old, or maybe 70 years old. And he remembers about vacuum tubes. Furthermore, he has the old vacuum tube manual on the shelf. He pulls it out, and he knows what tubes. The only place you can buy vacuum tubes, incidentally, these days is from the Soviet Union. Basically. Excuse me, the former Soviet Union. Well, that says that there is a body of knowledge outside of the narrow specialty that is useful. You can fall back on it to solve problems that are unusual. And our expert systems don't have that. We have not given them that knowledge. Now, down here, there's a much broader body of knowledge, which has nothing to do with Ohm's laws and Kirchhoff's laws and engineering principles and vacuum tube manuals. It has to do with plain old common sense. There are a lot of problems that we want AI problem solvers to solve that need to know about common sense. You need to know, for example, that if you knock over a glass of water, that it's going to spill and there'll be water all over the floor. And you don't read about that in any physics textbook. There are no equations that say you knock over a glass of water, or even better, you knock over a jar of ketchup and it's going to stain your rug. So you need to know a lot of common sense knowledge to solve some problems. And nobody has been representing, up until the 90s, had been representing common sense knowledge for machines. Now, the researchers in the 90s hold the view that the knowledge bases of AI programs have got to get much larger than they are. Because of the knowledge principle, there is no way out. It's difficult, it's a pain in the neck, it's expensive, it means harnessing immense amounts of human endeavor to do it, but we don't know any other way. It would be great if AI programs could learn much stuff, but they don't learn much stuff, and no amount of neural network stuff that I've seen even comes close to learning the stuff that needs to be learned here. Secondly, there's got to be a capability of the programs to reason at a more basic level, the level of principles of physics, principles of engineering, principles of any domain, and abstract models, generalized abstract models. Both of those, working with principles and working with models, allows these expert systems to parachute down to a soft landing when they fall off the edge of this plateau. Expert systems are known to be brittle because when you get to the edge of what they know absolutely nothing, and they fall precipitously 90 degrees from high levels of expertise to nothing because they don't know anything. Principles and models constitute a parachute for a soft fall. Now, research today is being directed at what is called model-based reasoning. Secondly, at knowledge representation methods that allow for scale-up so that this large knowledge-based dream can be achieved. Thirdly, some additional fundamental issues in knowledge representation, which are only now being seen and were not addressed in the 1980s. And finally, a view and a vision called knowledge sharing. Knowledge sharing starts with the idea that the largeness of knowledge bases will not be achieved by all of us agreeing on a set of conventions and putting all of our knowledge into one giant national knowledge base. Rather, we are going to achieve our dream by having a large number of distributed knowledge bases communicating with each other and able to understand the content of each other's knowledge bases with communication protocols, knowledge protocols handling the interaction between the different knowledge agents. I'll come back to that a little bit later. Let me talk about this level of general knowledge. Those of you who saw the public broadcasting program last night on AI realized that the theme that the editor who put together that program was pushing was that common sense knowledge, in particular the work of a research group at MCC in Austin, Texas, headed by Douglas Lennon, research group called the SITE group, was really the savior of AI because of the large amount of common sense knowledge that it was collecting. Lennon's group is attempting to represent a very broad swath of consensus, what they call consensus common knowledge, common sense knowledge. That common sense knowledge upon which we would all agree. They've also, and the amount of that knowledge that they've collected to date is currently about 10 to the 7th things. In other words, a very significant advance over previous knowledge-based systems. Although there is one knowledge-based system which I didn't mention before, which had already gotten up to 10 to the 6th things. That's a commercial development of an early expert system internist. The commercial development is called QMR, for differential diagnosis in internal medicine. So Lennett's group is already almost one order of magnitude at least, and moving toward 2 orders of magnitude greater than QMR, and 3 or 4 orders of magnitude more knowledge than any other of the normal expert systems have achieved. They've also collected dozens of special purpose inference methods to deal with different kinds of problems that you face in common sense reasoning. In other words, they're not aiming at a single uniform kind of theorem prover that will reason about all kinds of common sense, all the different kinds of common sense problems. So without elaborating on Psych too much, because it's not mainline to my talk, let me just give you an example of their car buying scenario, a common sense reasoner which helps you buy a car. As it asks you questions about yourself and your family and your life, if you answer some questions about the nature of your family, it should know from that what kinds of facilities and features in a car you need. Or when it asks you about where you live, it should know a lot of things about your geographical rationale. It should be able to figure out whether you need to buy an expensive traction control option, for example, or whether you need all-weather tires for your car, which is another expensive thing, or whether it makes sense to suggest a convertible for you, or what kinds of space you need in your car, depending on your family and the ages of your kids. And all of that's common sense knowledge, which we know, but most computer programs don't know. Now, it takes a tremendous amount of courage to work in that area, and most of us have not had that level of courage or that level of funding to work on, to employ that many people called knowledge enterers. The courage comes in believing that you can conceive of that many ideas for how to represent common sense knowledge. So some of us have turned our attention to a smaller, more controlled domain in which we feel we do know a great deal, and that is the world of engineering knowledge. Now, in the world of, so for engineering knowledge, we're particularly concerned with the world of mechanical engineering knowledge, electrical engineering knowledge, occasionally some chemical engineering knowledge. Fundamental to engineering tasks, whether these tasks are tasks of design or diagnosis or prediction of behavior, which we never used to have a fancy word for, but now we call simulation, prediction of behavior. Fundamental to all of those tasks is how things work. The cognitive act is to figure out how a device works, given physical laws and engineering principles, before you can decide how to design it better, or to diagnose it, or to predict its behavior. Let me use my own project at Stanford as an example. The How Things Work project starts first with the formulation of device models. We have to be able to describe to a computer program how a physical artifact is actually constructed. Unambiguously describe the structure of the device. Of course, we would also like to describe the function of the device in perhaps some abstract terms, what it is supposed to be doing. And then describe in a lot more detail the intended behavior of that device, given that structure, given the intended function. Actually, how does the device work? How is it supposed to behave? We call that the expected behavior. We're seeking to develop the technology for doing that for engineering devices for use in many different systems for many different kinds of reasoning tasks. One of the problems with the first generation of expert systems was the inability to reuse what we did. Every expert system was born as if it were a cottage industry, the result of a cottage industry. It was brand new, There was no reuse of anything. Secondly, we'd like to construct reasoning methods that will work with these kinds of representations of devices and representations of physical principles for core engineering tasks. And in particular, the core engineering task that we are concerned about is the task of simulation. That's partly because some background in our lab made simulation the most comfortable task, particularly the combination of qualitative and quantitative simulation. But also because simulation plays a big role in the thinking of our major sponsor, which is DARPA. That is, there's a very large activity in the area of simulation initiatives. In an era in which we are going to be spending almost nothing on military equipment, it behooves the military to simulate the newly designed military equipment, since you're not going to build it, but you still want to know how it behaves, to simulate it and make design changes along the way so that if you actually need the equipment at some point, you have well-designed equipment. You laugh, but that's a serious motive. So we're aiming at the qualitative modeling to allow the applicability to partially completed engineering designs, one where the model can be reformulated rapidly, and where the simulation procedure is self-interpreting. That is, to use expert system terminology, there's an explanation module associated with the simulator, with the physical predictor, such that the simulator can read the output and tell you how your device is actually behaving or misbehaving. The work is real. It's not hypothetical. We're experimenting with some things given to us by our NASA sponsors, the electrical power system of the Hubble Space Telescope, and a reaction control system for the space shuttle. We also have a number of other projects, some joint with mechanical engineering, like the problems having to do with the design and redesign of a robotic manipulator, which I'll mention a little bit later on because it's an interesting story. The collaboration, incidentally, is also with a number of other laboratories in the Palo Alto area, collectively known as the Palo Alto Collaborative Testbed, or PAC. Here's how humans do simulation now. It's important to see this so you have a baseline for knowing where I'm going. Humans formulate the simulation model. They get computers to run that model for them. They watch the behavior, and they formulate the description of that behavior. Almost all the thinking in the traditional simulation mode is human thinking. Humans do this, humans do this. In the work we're doing now, where the program is called Device Modeling Environment, the idea says that if a program is able to represent the structure of a device, and if the program knows a great deal about physics, and it knows a great deal about the equations, the physical principles underlying the physics, then it should be able to formulate the model for itself. You don't need to tell it what the model is. It should think of the model and write the equations. Now, at the moment, we're dealing only with ordinary differential equations, not with partial differential equations. But the program formulates the ordinary differential equations models. Sometimes it has an incomplete formulation, in which case it has to do some qualitative reasoning. Runs these through a simulation engine, which is a combination of qualitative and quantitative reasoning. The result of that is fed to an explanation module, which feeds back to the human some explanation of how that device works. That allows the human to say, uh-oh, I guess there's something wrong there. I didn't intend it to do that. In fact, our system will give him or her, the designer, a comparison between expected behavior and actual behavior of this device in the simulation. The human can then make changes to the model and run it again. I'd like to spend just a few minutes before I get to knowledge sharing telling you about context-driven model formulation, because that turns out to be one of the most interesting parts of this model-based reasoning path. There's a young graduate student, Pandu Nayak, who's working on this problem for his PhD thesis. The objective of Pandu's PhD thesis is to allow the program to construct what we call an adequate model for a given task. That is, by adequate we mean from a selection of possible ways of conceiving of components of a device, what's the right one? What works? What would be considered an appropriate model versus a stupid way of looking at the problem? How does a program select the appropriate way of looking at the appropriate way of modeling device? The key idea here is that you have to pay attention to the context. For example, here, you would model, let's take a pipe, a metallic pipe. You would model a metallic pipe, for example, as a physical support if there was some superstructure in the context that the pipe was supporting. But on the other hand, if it's connected to a water tank, the pipe is likely to be a flow channel. And if it's connected to a battery, the pipe is likely to be used as a conductor of electricity. It just depends on the context. You have to figure out what the context is in order to figure out how to model something. Well, let me give you an example. I'm going to show you, incidentally, this is only one example of about 30 examples that Pandu has worked out for his thesis, so this is not a unique case. I just picked a very simple one for this lecture. You look at this device. This is a very simple device. All of you engineers can figure this out in 8 microseconds. Got it? The thermistor is immersed in the body of water whose temperature you want to measure. Because the thermistor is a temperature-sensitive resistor, current changes in the circuit connected to the battery. The wire heats up, heating up the bimetallic strip, which pushes the pointer. Okay? That's easy. The critical thing to observe here is that the wire is being used here as a resistive element. As current changes due to the thermistor's change in characteristics, more current is flowing through the wire, and the wire is being used as a heater. Keep that in mind. Wire equals heater here. Now, let's take the same setup here. Is wire equals heater active here? This is another temperature gauge. What happens here? Here, the wire is not being used as a heater. Because of the context of the permanent magnet, the wire being wrapped around a piece of iron, the wire here is being used as a coil in which to create a magnetic field, to interact with the magnetic field of the permanent magnet, and thereby deflect in the magnetic field. Notice, incidentally, so the program, in being given a structural description of these two devices, the program has to figure out that in one case the appropriate model of the wire is magnetic principles, the other is heating principles. Notice, incidentally, that there's a third thing about a wire in there. Can anyone see the third wire? It's the spring. And that has torsion characteristics. That has nothing whatever to do with heater and magnetic characteristics. It's simply rotational torsion. Well, needless to say, Pandu's program figures that all out. Let me just show you the hierarchy here. Here, this happens to be the what we call a little bit of ontology. This is the ontology for the possible uses of a wire, possible models of a wire that Pandu's program knows about. His program knows about something like 300 to 400 other models of other things besides wires. So it's a non-trivial search space that his program is searching through. Down at the bottom you see, here's the rotating wire, the torsion spring use of the wire. There's the resistive use of the wire up there on the top. In passing, let me just say that AI people call hierarchies of terms and relations like this an ontology, a very strange term. It's probably not even a correct use of the philosophical term ontology, but AI people seem to enjoy it. So they call these collections of concepts and terminologies ontologies. I'm going to come to that at the end of my talk, which is concluding immediately. Now, in Pandu's program, here are some examples of rules that deal with model formulation. For example, if you are examining the structural context of a component, then if you look at the various connections in the structure, if a wire is connected to a voltage source, then model the wire as an electrical conductor. Let's look at a behavioral context. There's a very interesting one here. If the electrical power loss in a resistor exceeds a threshold, then model the resistor as a thermal resistor. Now, what that means is that rule allows you both sides of that. That is, you sometimes want to model a wire as a non-resistive wire. But if the voltage drop across the wire exceeds some threshold, it becomes implausible to model it as having zero resistance. You have to introduce a resistance. And then it becomes a thermal resistor. So that's the threshold that's here in this rule. So Pandu's program is a rule-based program of this sort, and it goes through and reasons through its space of models using the structural and the behavioral context to figure out what are the appropriate models. Let me conclude the talk by talking about knowledge sharing. I mentioned already that the typical expert system of today consists of tens of thousands of facts and heuristics, knowledge elements. Now, larger problems will require enormous amounts more of knowledge. For example, suppose we wanted to create the knowledge bridges between the many expert systems in medicine to provide basic medical knowledge about human biology, biochemistry, physiology, anatomy, disease processes, psychological processes, and so on. That would require not tens of thousands of things to know, but literally millions and millions of things to know. To build such knowledge bases, we face a huge task of knowledge engineering, knowledge acquisition, and we don't have much computer assistance to aid us. The knowledge-based systems research community is gearing up for a very substantial effort right now at inventing the technology for the development of very large knowledge bases, trying to create the tools that will facilitate knowledge sharing. Knowledge sharing means more than just the knowledge bases of several expert systems interoperating to solve a problem. Knowledge sharing also means the computer-facilitated cooperation of many people in the building of a large body of knowledge. The vision is one in which hundreds or thousands of knowledge-based builders cooperate in the building of a large knowledge base. Now, let me just give you an example of some knowledge-sharing activity that has been done at the outset of this program. In this program, this research activity on knowledge sharing, which is part of the DARPA Knowledge Sharing Initiative, one of the most significant, I think, of the recent DARPA initiatives, there are two things that people are tackling: the problem of heterogeneous representational languages and the problem of heterogeneous ontologies. It simply means this: we all have our favorite representational language. For some people, it's Loon. For other people, it's Classic. For a large segment of the commercial world, it's key or some other similar commercial knowledge representation language. Everyone likes their own. They like the features of their own language. Nobody wants to be disciplined into a standard representational language. Can't we use translation techniques to be able to facilitate, computer aid, the translation from one representational framework to another? The answer is we think so, and there is a good deal of work underway right now in a set of languages under the general heading of Knowledge Interchange Format, KIF. Secondly, even if we were able to do that, we still don't have much of the problem solved unless we were able to agree on the terminology, that is the vocabulary, and concepts of a particular area of work. For example, if we all meant different things by momentum or energy or force, we couldn't do much mechanical engineering together. We better have a pretty common agreement on what these terms mean, what the concepts mean. When I talk about a resistive wire, we better have the same thing in mind. Otherwise, we can't really deal together. My knowledge base can't talk to your knowledge base unless we share a common ontology. Now, fortunately for us, we're in the area of engineering, where most of us, almost all the time, mean the same thing by the words that we use as other people in engineering. And similarly, when we go to Japan or Europe or Russia or China, the engineers there mean the same thing by resistive wire as we mean. So we're in a relatively fortunate situation in dealing with engineering, but it's still a major problem. I gave a talk like this once as a keynote speech for the American Society of Mechanical Engineers Division on Computation. At the end, I was visited by a group of people representing the mechanical engineers who contribute their volunteer work to aiding the field. Normally, their volunteer work for most of the 20th century has been compiling the steam tables that go into the mechanical engineering handbooks and the pressure vessel tables and all of those other mechanical engineering things. And this group of people said that they found that very boring, and they would much prefer to aid the field of mechanical engineering by codifying the knowledge of mechanical engineering in just the ways I've been describing. And they volunteered 300 people to do that. Now, suppose those 300 people showed up on my doorstep tomorrow. I would absolutely have to have an ontology to give them, or 300 people could not collaborate on mechanical engineering. The first thing I would tell them to do was to create the ontology for mechanical engineering. Agree on all the terminologies and all the relationships between terms in mechanical engineering. That's step one. So that's the homogeneous ontologies problem. Now let me tell you a little story with which I'll close my lecture. This journey of 1,000 miles in the old Chinese proverb begins with a single step, and this single step was done at Stanford, in the Stanford area, last summer and fall, demoed to DARPA in early October of 1991, and was essentially the demo that triggered the knowledge sharing initiative. There's a collaborative group of people. The PAC group that I mentioned before consists of a mechanical engineering group at Stanford. Under Professor Kukowski, we call that the Next Cut group. Next Cut is a system that is AI applied to mechanical engineering design. There's Professor Genezareth's group, collaborative with Hewlett-Packard, which deals with digital design. There is the group that Professor Weitz and I run, which is the How Things Work group, doing the DME activity that I told you about. There's a group at the Lockheed AI Center under Bill Mark that has been doing work, among other things, an expert system to do the design of software for controllers for devices. That's called Envisage. In the PAC demo, the device that we were redesigning, it was a redesign scenario. The device that we were redesigning was an actual device that had been engineered, designed using NextCut by Professor Kukowski and his students to an industrial spec, over the past couple years before the demo. And what we were doing was redesigning that manipulator. It was a planar manipulator with two hands that came and grasped something and moved it in a plane to somewhere else, using motors, using linkages, mechanical linkages. I think they were 5-bar linkages to move the object around. In this particular scenario, the human designer decides that what is necessary is to move an object faster in the plane than was being moved before. Let me just review the actors in this drama. Next Cut knows the original mechanical engineering design of the arm. It knows the dynamics of that arm, and it also knows the machining of that arm, how the parts were actually machined. Design World knows digital electronics, but it also keeps a parts catalog for everyone else, so it's also an engineering parts house. DME knows about power supplies because we've been working on the power supply system for the Hubble Space Telescope. It knows about power supplies and motors. It knows about the sensors that detect the movement of the arm. And it also knows how to do qualitative and quantitative simulation. And finally, Envisage knows about software controller design. A low-level knowledge exchange language, KIF, has been worked out, as well as a knowledge sharing communications protocol called KQML. And these collaborate over a network, which happens to be the internet at the moment, which we call the knowledge bus. Also agreed upon by the collaborators was a shared ontology for this robotic manipulator task. We spent a lot of time on that shared ontology. In the demonstration, in the task of redesigning this arm, Envisage, designing the controller software, sent a request to the other systems for knowledge of the dynamics of the robotic arm. Next Cut, the mechanical engineering system, fielded that request and sent the information. Then Envisage asked all of the different agents on this network to perform necessary simulations of the robotic arm given their little piece. Now, our DME, since our expertise was in motors and power, our DME, doing its simulation, found that if you tried to speed up the motion of this arm, you would put so much current into these previously designed motors that the motors would burn out. So DME sends a message out to the system that says the motors will burn out. The human power subsystem designer watching all of this says, uh-oh, I've got to replace that motor. And he picks another motor, a larger model. The change notice from the human designer was picked up by Next Cut. Next Cut noted that the fixtures that hold the motors might need to be changed. It reasons that if you have a larger motor, you're going to need a larger shaft, possibly. And if you need a larger shaft, you're going to need a different fixture of that motor to attach to the manipulator. So it sends a request to Design World, to the parts catalog, saying, could you tell me more about the specs of this larger motor? Design World supplies the geometry of this from the parts catalog. This supplies the geometry to Next Cut. Next Cut says, oh yeah, now I can redesign the fixturing. So it redesigns the fixturing to attach that to the arm. Meanwhile, Envisage is watching all of this, and it figures out what the new controller dynamics needs to be, and therefore what the sensor signals will be, and therefore what kind of digital electronic spec it needs for a special purpose chip, or actually a PC board, that will handle these sensor signals. And it sends that to Design World. Design World knows digital electronics, so it designs that circuit board out of chips. And then Envisage finishes its activity, and that's the end of the demo. Now, 15 different computers located at various sites on or near the Stanford campus were actually used for that experiment, for that distributed environment. Each system ran on its own hardware base and its own software base. Each system had its own knowledge base. That was a deliberate design decision in order to investigate this whole idea of scalability in a distributed way. There was no central system in all that knowledge that was accessed. Now, this is a fragile little seedling, but what is it a seedling of? In 1986, a group of us met at the Center for National Research Initiatives, Corporation for National Research Initiatives, Bob Kahn's research organization in Reston, Virginia, to hold a conference sponsored by CNRI on the creation of a national knowledge base. Marvin Minsky was there, and Marvin and I were engaging in an exercise trying to envision what this great knowledge base in the sky was going to be like. We called it the Library of the Future. And Marvin, and what we imagined was we were standing somewhere in the year 2035, 2036, looking back 50 years at 1986 and asking ourselves what change had been made. And Marvin said something very interesting. He said, looking back at 1986, he said, "Isn't it amazing? They used to have books that didn't talk to each other." Our packed experiment really is the first instance of the books talking to each other. I think that is a sign of things to come. And I think that will become a very important act for this drama of knowledge-based systems. A collection of knowledge bases that together constitute a national resource, particularly in the promotion of engineering, but in the promotion of the common sense applicability of knowledge to a wide variety. That is the application of common sense knowledge, not only engineering knowledge, to a wide variety of different tasks that need to be supported, human tasks that need to be supported by computers. Thank you.